May I begin? Great. Well, thank you everybody for coming. My name is Mark Jankauski. I'm very excited to be here today. I'm going to be discussing a little bit about the research I've been working on for about the last year and a half, and that's regarding dynamic modeling of a rotating insect wing. So first, I'd like to begin with an outline of the presentation, a little bit of motivation. First, why we believe there is some amount of utility to this model, and really how we feel it's unique from some of the existing models. Then I'll step through the model formulation, ultimately how we developed this model of a rotating insect wing, after which I'll apply it to the forewing of a Manduca exsexta, which is kind of the classic flying insect, also known as a hawk moth. After that, we'll look at a couple of the key results that we found, and I'll briefly conclude the presentation with just a brief summary of the results. So first, let's talk a little bit about the motivation, why we started this research. Obviously, the study of flapping wing research has a lot of applications in both engineering and biology. So for engineering, flying insects often tend to serve as the paradigm for small flapping wing style microaerial vehicles. And this is because they're really capable of doing kind of evasive maneuvers while maintaining this robust stability. So for biologists, this research provides insight into the sensory motor coordination of insects. So some of you might know that insect wings are richly imbued with what we call mechanosensation cells, which from an engineering standpoint really behave similarly to something like a strain gauge. And it's believed that a large amount of the neural feedback that an insect receives during flight is generated through the strain in these, basically in these cells. And it's our belief that if we're able to basically model this and interpret this in a similar way to an actual flying insect, this might facilitate designing control systems for small flapping wing microaerial vehicles moving forth. So prior to beginning this research, we did a brief literature review just to kind of see what models were available. And we found that there's several unique models out there, but they generally fell into one of two categories. And this was either the rigid body model or the finite element model. So the rigid body model treats the wing as a single rigid, undeformable structure, and really has a number of benefits associated with this. The first is that it retains a low number of degrees of freedom. The benefit to this is if you're trying to do something like a parametric study, the computational time required to solve something like this is very, very small. Furthermore, if you treat aerodynamic forces as kind of as generalized forces acting on the wing, you can predict some of these aerodynamic parameters, such as lift and drag, which are of course of interest to people that are designing microaerial vehicles. But kind of the disadvantage to such a model is that you're unable to really estimate the localized strains that are developed within the wing during flight. So obviously these models have limitations in terms of biological studies of the neural feedback an actual insect is receiving. So the other subset of models then is the finite element model. Now the finite element model is of course capable of predicting these localized strains, but unfortunately it's only really capable of describing infinitesimal rotation, which of course has limitations as the rotations of an actual insect tend to be very, very large. Should you try to include these large rotations directly in finite element modeling, the result will be a time-varying stiffness matrix. So basically, this stiffness matrix must be updated at every single time step during your finite element analysis. And the result of this is an enormous amount of degrees of freedom, basically making a direct finite element approach computationally infeasible. So the aim of the proposed research then, shown in blue here, is to really synthesize the benefits of each of these two subsets of models into one comprehensive dynamic model of a rotating insect wing. And we'd like this to have the following three important characteristics. One, we'd like this to remain or have a low number of degrees of freedom, such that we maintain this computational practicality. Second, we'd like to be able to predict the localized strain in the wing, such that we can use such a model for the insect neural feedback studies. Third, we'd like it to be able to accommodate arbitrary geometry. And what I mean by that is I'd like this to be able to be applied to not just the forewing of a hawk moth, but rather anything that flaps its wings. So before talking about how the model is developed, I'll mention the assumptions that are made. First, we've assumed that the in-plane deformation is small. So all the elastic deformation is assumed to be out of plane. Second, we're going to assume that the deformation of the wing is entirely a result of inertial elastic effects. So we'll be neglecting some of the aerodynamic effects that a lot of the other researchers have been presenting here during this conference. So now that I've kind of spoken about the motivation behind this research, I'd like to talk about how the model was formulated. So the first thing that we've done is basically treat the insect wing as a deformable body subject to three-dimensional rotation about a fixed point on the insect's body. And this is really where the forewing meets the body, as you can see here. And so we've established two finite rotations, roll, which we've called alpha, and pitch, what we call beta, to establish a rotating reference frame that rotates with kind of the dominant rotations of this wing. And how this is set up is basically we've set this in the standard IJK kind of coordinate frame. We perform the roll rotation about this axis here, which transforms us to what we call the prime coordinate frame. Then we apply the pitch about the J prime axis, and that kind of transforms us into this last coordinate frame then, which is the double prime coordinate frame, which we'll use throughout the remainder of this formulation. And some basic geometric analysis then shows that the angular velocity is this expression on the lower left-hand side. So the third rotation that we've implemented then is this yaw rotation, which I've unfortunately forgot to draw on the figure, but this is going to occur about the K double prime axis here. And basically, this will not be considered in the rotating reference frame. It's considered very small. And what this basically allows for it to happen is the wing can really yaw within the rotating reference frame. So now that we've established this rotating reference frame, I would like to draw a position vector to some differential mass element, which will ultimately be integrated over the entire mass domain of this wing structure. And this is really comprised of three intermediate position vectors. Position vector R1 then is the planar position of the differential mass element without regards to the yaw rotation. So then vector R2 basically considers the infinitesimal yaw rotation. And again, we're considering this to be small, so we've employed some small angle approximations here. And the last and probably the most interesting position vector then is R3. And this is representing the infinitesimal out-of-plane elastic deformation of the wing. And this is contingent on both position and time. So essentially what we've done here is we've superimposed an elastic deformation on top of the large rigid body motion of the wing. And of course, you can sum these three vectors to give you the total position of the differential mass as a function of time. Okay, so I don't want to get too much into the mathematical detail here, but I'll point out a couple major features as to how the model was developed. And in my opinion, the single most important feature is the eigenfunction decomposition of the elastic deformation. So ultimately what we're doing here is we're decoupling the time and position dependence. And the benefit to such a decomposition is that we're able to find the position dependence entirely through finite element. And this is called the mode shape, which we've denoted by the letter phi. So really the only remaining variable to fully characterize the dynamics of this rotating wing is the modal response, which we've denoted by the letter qk. And really that's just the time response of one of these mode shapes. So to formulate the equation of motion that governs these modal responses, we've basically come up with expressions for the kinetic energy, indicated by T, and the potential energy, indicated by V. And we'll use Lagrange's equation with these energy quantities to essentially figure out what the equation of motion for the kth mode shape is. We've also defined two vector quantities here which relate to the inertial force center. The only reason I've presented these is because they'll show up in the equation of motion. So after applying Lagrange's equation, we've ultimately found that this is the equation that represents the time response of the kth mode shape, or when solved, represents the time response of the kth mode shape. And so you'll notice two important characteristics of this equation. First, it's time varying. And the time variance is introduced through the stiffness term. So this is kind of a meaningful result because the average stiffness over a single wing beat will actually be a little bit lower than the natural frequency of the same static wing. So this basically reduces the natural frequency slightly. The second meaningful result then is that it's linear. And what this allows us to do is really look at each response subject to each excitation term individually. So we can kind of decouple some of these excitation terms. So what are the excitation terms then? We've identified 3 that are common within a rotating reference frame, and that is the Euler force, which is really just due to the acceleration of this coordinate frame, the centrifugal force, which tends to draw the body away from the center of rotation, and lastly, the Coriolis force, also called the gyroscopic force. And this occurs when there's relative motion happening within a rotating reference frame. And in this case, that relative motion occurs because of the yaw rotation, which was, again, predicted as, or assumed to be small. So now that I've formulated this model, I'd like to apply it to, or I'd like to show you how to apply it. And to do so, we've basically dreamt up an example wing that's similar to that of the forewing of a hawk moth Manduca sexta. Now, I'd like to emphasize the point here was the goal was not to perfectly emulate this wing, but to rather capture a couple of the essential characteristics, namely the first few natural frequencies. So how we basically dreamt up this wing was we traced CT images of an actual hawk moth wing in finite element, or Abacus finite element software. We replaced the membrane material with a paper material of uniform thickness, and we've neglected the venation pattern. We've also implemented a camber geometry with about 13%, which is certainly exaggerated from that of a real insect. And we notice that this has the effect of lending support to the first bending mode. So really what you're doing is you're increasing the natural frequency without changing the mass or altering the actual stiffness properties of that wing. And what we found was our finite element model, really despite all these simplifications, estimates the reported values of an actual hawk moth wing within about 5%. And you'll notice the values here are about 63 and 87 hertz, and those numbers will become an important factor in a couple minutes here. And this image here shows the mode shapes of the first 2 modes. This is the first mode, which is a bending mode, and this is the second mode, which is a twisting mode. So for this example, we'll just consider these first 2 mode shapes. So the next thing that we'll do is assume some rotation profiles. So the formulation basically can accommodate arbitrary rotations, but for sake of simplicity, we'll assume that they're harmonic and in phase at this time. So these are the rotation amplitudes for an insect in forward flight at about 5 meters per second. This is just taken from the literature, and certainly you can use any rotation amplitudes that you'd like. And the driving frequency that we've used is 25 hertz, which is consistent with that of an actual hawk moth in both forward flight and hovering flight. So now we'll take a look at some of the excitation terms, or really all of the time-varying terms in this equation. And kind of the important feature that we'd like to look at here is the frequency content associated with each time-varying parameter. So as I mentioned earlier, the stiffness is time-varying as a result of this centrifugal softening effect. And we found that that actually occurs at about twice the driving frequency of the wing, or twice the flap frequency. The Euler force oscillates at about the driving frequency and has depreciating superharmonics at twice the driving frequency, 3 times the driving frequency, etc. Perhaps the most interesting result we found here then is the gyroscopic force, or the Coriolis force, which oscillates at exactly twice the driving frequency. And this value actually falls very close to the first natural frequency of the wing, indicating that there might be some amount of resonance activated here. And furthermore, this actually occurs kind of in sync with the stiffness term, meaning when the Coriolis force is at a maximum, the stiffness is at a minimum. So that's kind of an interesting result, as you're kind of pushing harder as this thing is softer. And lastly, we found that the centrifugal force oscillates at the driving frequency and 3 times the driving frequency, where 3 times the driving frequency is falling near the second natural frequency of this. So again, we kind of have these resonance effects now in the first 2 structural modes of this wing. So this slide here will show the modal responses simply for the first mode shape. I've not shown the second mode here. You'll notice that the Coriolis force generates the largest response, and that's, again, because we're operating kind of near this resonance point. The centrifugal force, then, which is not shown, is, for the same reason, generating the largest response within the second mode shape. And interestingly, because of the proximity of the forced vibration and the free vibration, we've observed a beat phenomenon. So this is the beat phenomenon just generated by the Coriolis force, and then of course we can sum all these results together due to the linearity of the equation of motion to give us the total response, which, again, since it's dominated by the Coriolis force, also reflects this beat phenomenon. So we found this to be very interesting, that there was the beat phenomenon occurring actually both in the first and second mode shapes. So we wanted to look a little bit more into this. Now, there's a professor at UCLA, a guy named Mark Fry, who hypothesizes that a large amount of strain generated by the gyroscopic forces really is one of the driving mechanisms in providing feedback for an insect during flight. And therefore, the beat phenomenon might also have kind of this same biological significance. It's our belief that the beat phenomenon may potentially be used to identify the yaw or other rotation amplitudes, and potentially be used as maybe a yaw rate sensor. Thus, it seems that if we're able to interpret this feedback in a way similar to an insect, we might be able to supplement traditional accelerometer or gyroscope-based control systems, perhaps with a strain-based control system, which of course might be smaller, lighter, more conducive to an actual microaero vehicle. But of course, there's a number of factors that could potentially affect the beat phenomenon, which would, of course, kind of destroy our null hypothesis. So we did a bit of a sensitivity analysis to see how sensitive this beat phenomenon was to a number of factors. I think there's more introduced in the conference paper, but today, due to time, I'll just talk about the effect of changing the yaw amplitude and introducing damping, which was neglected in the initial formulation. So the first thing we'd like to address in the sensitivity analysis is the yaw amplitude. And what we've done to basically look at the yaw amplitude is we fixed the pitch and the roll amplitudes according to the forward flight values that we presented earlier. We've then varied the yaw amplitude from about 0 to 0.3 radians, where the typical operation point in forward flight mentioned falls at about 0.2 radians. We've then gone ahead and solved the equation of motion, and then identified really how much each force constitutes the total response, or contributes to the total response, with the idea that if the Coriolis force, at least within the first mode, tends to dominate, then the beat phenomenon should be preserved. And as you can see, at the operation point, the Coriolis force is really constituting about 70% of this total contribution. And really, it's insensitive to small variations about this value. So if you were to increase the yaw amplitude or decrease the yaw amplitude slightly, you'd notice a pretty insignificant change in the overall contribution of the gyroscopic force. So a second factor we'll look at is damping. Now, the beat phenomenon is basically, like I mentioned, the interaction between the free vibration and the forced vibration of the wing. The forced vibration being that generated by the Coriolis force. So in general, structural damping tends to cause free vibration to die out over time, which, of course, based off of this formulation, would cause the beat phenomenon to die out over time as well. So really, to test this hypothesis, we've introduced a modal damping of about 1% and solved the equation of motion numerically, just to kind of see what result we got. And of course, you can see based off of this figure, the beat becomes indistinguishable within 1 second, which of course is problematic to our hypothesis. So we began asking ourselves, are there potential mechanisms by which the beat phenomenon could be preserved? And we found that there are. The first is basically randomizing these yaw rotation amplitudes about some mean value. And really, this is probably more reflective of actual insect flight. Of course, these aren't machines in nature, so they aren't going to have a perfect rotation amplitude every time. And by slightly randomizing this value, we found that we reintroduced the free vibration of the wing, and thereby we kind of maintain this beat phenomenon. And another way that this could potentially be maintained, or the free vibration could potentially be maintained, which again is not accounted for by our model, is quick translations of the insect body. So if the insect was to start and stop, basically the free vibration would be reintroduced, and that would cause the beat phenomenon to persist. So in biology, I guess this would lend itself to being beneficial for an insect to kind of moving around frequently, which you can kind of observe if you watch any flying insect. So the last component I'd like to talk about then is, of course, strain. Since strain is what we're ultimately selling here in terms of feedback mechanisms, I'd like to show how you demonstrate strain using this model. And so the strain from each different mode shape can be determined explicitly in finite element analysis. You'll notice this figure on the right is the strain for the first mode, both the two normal directions of strain and the in-plane shear. Then the total strain can be represented as a weighted sum of the modal responses, as indicated by this expression here. So for this example, we're just considering these first two vibration modes. And then we have to select some point of interest to really figure out how the strain evolves as a function of time. And so we've basically selected a point near the base where the strain is the largest to see, again, how the strain changes with time. So this figure to the right then represents the strain as a function of time, and you can see that this also reflects a beat phenomenon. So basically, even though we're kind of looking at the contribution of two different mode shapes now with two different frequencies, the beat phenomenon is still maintained despite kind of the interaction of these two modes. You'll notice that the x and y components of shear are very small compared to the in-plane shear, which tells us a little bit about the directionality of the shear. So really, since this is the dominant component, the maximum direction of shear will be about 45 degrees from the positive x-axis. So with that, I'd like to briefly conclude this presentation, just summarize some of the results. That was an inertial elastic model of a rotating insect wing was developed with the following key characteristics. First, it was able to maintain a low number of degrees of freedom, which in this case was just the retained number of modes. So for our example, two mode shapes. It was capable of predicting the local strains such that it can facilitate studies in insect neurological feedback. Third, it was able to accommodate arbitrary geometry. You can all see that now we can kind of design any wing we'd like within the finite element software, so this can really constitute any insect. The major premise of the model was by treating it as a deformable wing, subject to three-dimensional rotation about this fixed point. It was determined that the modal response was governed by Coriolis-Euler centrifugal forces, and that the Coriolis and centrifugal forces caused the beat phenomenon in the first and second modes, respectively. So lastly, we hypothesized that the beat phenomenon could potentially be used to facilitate strain-based control in flapping wing micro-air vehicles moving forth. We found that it was insensitive to small variations in the yaw amplitude. Of course, it does die out if you consider structurally damping, but again, there's various mechanisms that can be employed to basically reintroduce this beat phenomenon. And lastly, the physical strain from the first two modes also shows this beat phenomenon occurring. So I'd like to thank the National Science Foundation for supporting this work. I'd also like to thank my co-author, Dr. Steve Shen, who was unable to make it to the conference. And lastly, I'd like to thank the audience for your attention during my presentation. Thank you very much, and I'd like to open the floor to any questions.
So there must be many questions for Mark. We have time for a few of them. Rick.
Yes?
In the Delphi wing, when you compare the vacuum tests and the air test, we see that damping is very significant.
Sure.
The amplitudes in vacuum are much higher of the more flexible wing, probably, than the Hawkmoth. Do you think you can either incorporate that aerodynamic damping or aerodynamic forces? And how does that influence your
Well, that's a good question. I can't say, excuse me. The question was how do aerodynamic forces, or how can we possibly incorporate them into the model? Good summary? Cool. The answer is it's difficult to say. The reason that we've neglected it ultimately was there was some amount of experimental evidence in the past, an experiment where they actuated this in both helium and air, at least the Hawkmoth wing, and found that the deformation presumably was due to inertial elastic effects. So that's kind of the background as to why the assumption was made. In terms of actually implementing the aerodynamic effects in practice, again, that's not really my specialty. I'm not sure exactly how that would be done. We do plan to, while we validate this model, kind of do, again, a vacuum test in conjunction with an air and kind of look at these two results. And really, we think that the driving factor as to how valid this assumption is the different geometries of the wing. So certainly different insects might be dominated by aerodynamics, whereas some, like perhaps the Hawkmoth, are really a function or mostly dominated by these inertial elastic effects. But really, to answer your question, we're not entirely sure how aerodynamics will play into this, but we think there will be a number of other factors that really constitute the overall contribution of aerodynamics. Does that answer your question? Excellent.
Are there more questions?
Yes?
If I understood correctly, the mechanics is based on a linear bending model. Or you're taking into account the bending stiffness of the structure, but not the stretching.
Correct, correct.
Now this is a membrane, and membranes are primarily dominated by in-plane stresses.
Sure.
Stretching. So how good is this model considering this geometry?
Sure. The question was, membranes are typically dominated by in-plane stresses. So how, since we're neglecting in-plane stretching, how accurate is our model? So the answer to that is, although in-plane stretching was neglected, you can actually still get in-plane strains. And the reason for that is because of the camber geometry. So if you imagine you have two fixed walls and a bent arch between them, if you push down on that, the overall in-plane shape does not extend. Yet you still are able to generate these in-plane strains. So again, we believe that the out-of-plane deformation will be more substantial than the in-plane, but that's the mechanism by which we're able to get in-plane strain without actually considering stretching of the wing. Does that answer your question? Excellent.
So one more short question, perhaps. So I have one, actually.
Sure.
So you show that this beat mechanism can lead to an estimation of the yaw
Yes,
rate.
correct.
Do you see any mechanism for also estimating the other rates, pitch rate, roll rate, within the same principle?
So the question was, we've identified a mechanism by which we can identify the yaw rate, but can we extrapolate that to include the rate of, say, the pitch and the roll? The answer is not necessarily, not immediately, not based off of the analytics. There might be some clever mechanism by, say, system identification or some kind of more robust control algorithms, but just kind of looking at the form of the equation, from an analytics standpoint, it's not obvious how you would really extract those two rates.
So let's thank the speaker.
Thank you.